All right, so we'll get started. This will be our last lecture of this class. So let's get started with a few announcement or kind of reminder items here. All right, so remember number 11 homework is due on Monday at 12:50 during the day. Okay, so it's right after the noon. So original file, I forgot to attach figure to problem 6. Now it was there. It's there now. I did that yesterday. I added. So if you download the homework file earlier, you can check it online again with the new figure included. Okay, so this is 11, and then the next item, important item, will be final exam. It's going to be on Tuesday because we don't have a lecture on Monday, so you guys have to remind yourself. Okay, maybe set an alarm, maybe at 9:30 or something like that. So I probably can send you guys out the exam about at 9:30, so then you can start working on it earlier, and then you can submit by 12:30. Okay, on Moodle, there's assignment final exam over there. Now, usually if you run a little bit time over 12:30, that's fine too. Okay, so yeah, 10-20 minutes doesn't matter. Okay, if you need it, then use that. Okay. For the end of course survey, all right, I see most of you guys have done that. There's still a few of you guys haven't done. Okay, so if you get a chance, please do that. Although you wouldn't lose access to Moodle this time because we are having had to transfer or had to make the transition to online teaching and online learning. So even if you don't do that, it's okay. You wouldn't lose the access to Moodle this time, this semester only. Okay, but as the situation right now, we have been talking about if there may be chance that we wouldn't be able to go back on campus next semester, then we probably will still be doing online teaching. So um, do the survey and then put what you think about online teaching there, something we can improve over there. Any comments you guys can provide to help you better learning, that will be appreciated. Okay. And then no lecture on Monday. Okay, so that's the next reminder item. The last two here is not really related to this class, but I would like to take this chance to mention this too. So for fall 2020, physics lab assistant positions are still open. So this is physics 1. Okay, if you have taken University Physics 1 lab here, then you should be able to lab assist. Okay, so there are 4 sections, including 2 general physics, 2 university physics. Okay, they are all available. Okay, spring semester positions, they are filled already next year, but the fall semester, these positions are still open. If you are interested, let me know. Okay. All right, and then the last one here is starting from next year, next academic year, we actually will offer a physics minor. Okay, here. So if you are interested, let me know. So for you guys, for engineering folks, for your existing curriculum, if you want to get physics minor, so pretty much what you need to do is to take modern physics. Okay, so then you will get a physics minor. Okay, so if you are interested, you can also let me know. Okay, so these are the reminder items here, or a couple announcements here. Any questions you guys have?
For the physics minor, what else? So you said like you have to take more than physics, so like taking like dynamics and like all of that stuff, does that count as a physics minor, or what else, like what other courses would we have to add?
So the required for physics minor is either general physics 1 and 2 with calculus and modern physics, and then also it could be like university physics 1 and 2, and then modern physics and calculus. So you guys have taken university physics 1 and 2, and then calculus. So the only thing you need to take in addition is the modern physics. And then for electives, it's a bunch of your engineering classes, the dynamics, statics, etc. So your total hour will be 20 credit hours. So for you guys, most of you guys, or I think for all engineering students, the only extra class you have to take is modern physics, okay, to get a physics minor.
Oh, okay. Thank you.
Okay.
Dr. Ho?
Yes.
So the more than physics class, that's just, what is that? Just a three credit hour course or what?
It's 4 credit hour. So it's 3 credit hour lecture plus a lab component. Yeah, it's 4 in total. So if you need to take another like a class with lab component, you can take that too.
Okay, cool.
Yeah. All right.
Class actually called more than physics.
What? Say it again. Why it's called modern physics?
Is that what it? Oh, I thought you said more than physics.
modern physics. All right. So in modern physics, we'll pretty much talk a little bit about like quantum physics, relativity, etc., and then atomic physics. So something like introductory level. All right. Yeah, I like your background, Maria. It's you're outside. That's nice. Okay, so let's get started on the lecture here. Today we'll be talking about conservation of energy. So I think this is kind of review of what we learned earlier on conservation of energy. Okay, it's pretty much the same thing. Okay, so we'll first do the reading quiz. Okay, so go ahead and do the reading quiz. This is your last time for extra credit. Okay, so go ahead and do that. Send your response to me in the chat privately. All right, I think everyone has submit your answers here. So we'll take a look. So elastic potential energy is defined as, so it's 1/2 K S square. S is being the either compression or depression of the spring, okay, referring to its original equilibrium position. So the first one should be A. Okay, most of you guys got that one. All right. But it's positive, okay? It's always positive, okay? It's not going to be negative. And then 1/2 kV squared is the kinetic energy, okay? So, and then that's translational kinetic energy only, okay? So the second one here, second problem here says the kinetic energy of a rigid body consists of the kinetic energy due to, so two parts, translational motion and rotational motion, okay? So you will have translational kinetic energy, you also would have rotational kinetic energy, okay? So the second one will be C, all right, A and C, okay? All right, so then let's take a look on the lecture part. So the first here is about, so yeah, so this section is about conservation of energy. So this is nothing but it's actually an extension of work energy principle, okay? So it's from work energy principle. For the problems, you can use conservation of energy. You can also use work energy principle, okay? So in this case, if energy will be conserved, then you would have simpler scenario, which is the work is only done by conservative force, okay? So here again, the distance is a key indicator over here, okay? But you'll be looking at the and work done by all the forces. If the work done is purely from conservative force, then the energy is conserved, okay? So what's an conservative force? So it's if the work is done by the force that is independent of the path, okay? So say you can move an object from one position to another position using different paths, but at the end, the work done by a particular force is going to be the same, doesn't depend on the path, then that force is conservative force, okay? So as a few forces that we deal with in this class, they are the only conservative forces. One is gravitational force. The second one is the spring forces, okay? So I think that's the only two here we'll be dealing with, okay? And then the third one will be the electric force, okay, which we had that in the general physics or the university physics too, or the ones you are going, some of you guys are still going to take, okay? But those are the three forces commonly as the conservative forces, okay? All right. So if the work is done by conservative forces, then you can apply conservation of energy, okay? So basically, you have kinetic energy plus potential energy to be conserved, okay? So initial, the sum of kinetic energy and potential energy should be equal to final, the sum of the kinetic energy and potential energy, okay? Most of the other forces are not conservative force, okay? So for example, the friction force or whatever pulling force you have from the spring or whatever, okay, other forms of. But sometimes even you have not only conservative force, you would also have work done just by the conservative force because other force might be doing zero work, okay? We'll touch on that in a little bit, okay? But basically, you are doing T1 plus V1 equals to T2 plus V2 when you apply conservation of energy, okay? So T is the kinetic energy, V is the potential energy, okay? So potential energy could be gravitational potential energy, could be elastic potential energy in the spring, okay? So those are the two forms of potential energies. For gravitational potential energy, it's going to be just weight times the vertical position because it only depends on vertical position. It doesn't depend on the horizontal position, okay? So you want to choose a reference line where the potential energy is equal to 0. We call that as data line. Okay, so then if you are y above the data line, your gravitational potential energy Vg then is equal to weight times Yg. Okay, if you are below, then you are having negative potential energy. Okay. For spring potential energy, it's always going to be positive. It's going to be 1/2 Ks squared. S is the either the compression or deformation of the spring compared to its natural unstretched equilibrium position. Okay, where S is defined as 0. Okay, so the total length of the spring, you don't use that, but you use that minus the unstretched length of the spring. Okay. And that's always going to be positive, or at most 0. When you're at the natural position, then it's 0. Okay. All right. Now, when you apply conservation of potential, then you can solve for the velocity and then displacement, and then sometimes you might be looking for the force. Okay. So basically, you are to think about potential energy could have two forms. Okay, so usually when you have spring involved, then you have elastic potential energy. If not, then you only have gravitational potential energy. Okay, kinetic energy, you would have translational kinetic energy, 1/2 mvg square. You could also might have rotational kinetic energy, 1/2 ig omega square. Okay. All right. So let's take a look on a couple of concept quizzes here. All right, let's create the breakout rooms here. I have 3 and then automatically generate it. Okay. So join your room and then work on this too. We'll look at the answers in a little bit. All right, so you guys are back. We'll take a look at these two together here. First one says, what will be the change in potential energy? Okay, so so you take this as data line, original position here. So if it rolls 2 turns, 2 full revolutions, then you probably are somewhere here, down here. So for elastic potential energy in the spring, okay, this is the natural position, then it will be increased by 1/2 ks square. Okay, so you'll be looking at 1/2 k, so B shouldn't be right because the elastic potential energy should be positive. Okay, so 1/2 200, yeah, the rest has the same first term for elastic potential energy, so it has to be that one. Now also you want to look at the change in gravitational potential energy. So this guy rolls downward, so but gravitational potential energy should become negative. Okay, so if this is the data line, this is the initial 0 gravitational potential energy. So that change will be minus mgh vertical h. Okay, so then let's take a look here. The first one has plus, so then that's not going to be right because it should be decreased. Second one, we ruled that one out already, so it has to be C, okay? So C is M times G times 1.2 pi, which is 0.3 times 2 pi times 2. So it's twice 2 revolution times 2 pi r, that will be the distance traveled on the slope. Okay, so 2 times 2 pi times 0.3 gives you 1.2 pi, and then you do sine of 30, that gives you the vertical drop position. Okay, so it has to be C here on the first one. All right. On the second one, it says determine the kinetic energy of the disk at this moment. Okay, so at this moment, it gives you the initial velocity to be 3 meters per second. All right, so then so A will be 1/2 mv squared. That's the translational kinetic energy. Okay, but if it has 3 meters per second velocity down here, then it also rotate with a certain angular velocity, right? So if it doesn't slip, then the rotational should be 1/2 m r square. So let's see, mr square. Yeah, so it tells us kg is 0.5, so this is m kg square, that gives you I. So 1/2 I omega square. Omega is equal to V divided by R, so 3 divided by 0.3, that gives you this guy. Okay, so it has to be C because kinetic energy should consist a translational kinetic energy plus a rotational kinetic energy here. Okay, so answer A plus answer B. All right. Any questions you guys might have? So if that's clear, then we'll check on a couple examples here, right? So the first example here, it says the raw AB here has a mass of 30 kilograms. The spring is unstretched when theta is equal to 45. The spring constant is 300 newtons per meter. Find the angular acceleration of the raw AB when the theta is equal to 0. If the rod is released from rest when theta is equal to 45 degrees. Okay. So in this case, we'll look at the free body diagram and examine what's the work done by all the forces. Okay. We will realize that we can use conservation of energy because the energy work done on the rod should be just coming from the conservative forces of the spring force and then the weight. Okay, so we'll take a look at that. Actually, it doesn't gives us the free body diagram, but we can think about here. So there will be a force, spring force on this B point. Okay, pulling it this way. There will be a weight on the center of gravity here. There will be two supporting forces at point A and then at point B perpendicular to contact point. So that should be perpendicular to point A for the reaction force at about point A. And then on the reaction force at point B, that should be perpendicular to this groove over here, okay? So you can see at point A, this is moving in the direction that's perpendicular to the reaction force at point B here. So reaction force at point B should be doing 0 work. And then also on point A here, because this guy is moving downward, so reaction force should be doing 0 work as well, okay? So then only the gravity and then spring force will be doing work on the rod here. So then we can apply conservation of energy. So we'll be looking at the potential energy and then kinetic energy at the initial position and then final position, okay? So for the initial position, we can take the data line to be over there. So then gravitational potential energy is 0. The spring elastic potential energy should be 0 because the initial position is the unstretched position for the spring, okay? Now, at position 2, when this guy is laying down over here horizontally, when theta is equal to 0, so then your gravitational energy at position 2 here should be minus mg times this y over here, okay? So it's going to be mg, okay, and then minus y. So minus y, it happens to be at the center over here, which is 1.5 meters times 1/2. Now this data line, it should be, the graph doesn't quite indicate it's at the center, so we probably would indicate it over somewhere here, okay? So, but yeah, it just tells you that it should be at the center, okay? The graph doesn't show that, but it should be over there, okay? So then this y, if you take this data line when the rod is at the laying down position, then y will be minus, okay, 1.5 times sine of 45 degrees, okay? So this is the gravitational potential energy at the second position. Elastic potential energy at the second position should be 1/2 k s square. Okay, this is s. Now, the original length would be 1.5 cosine of 45 degree, right, for the spring length. So you want to do final length minus original length to be the change in length, okay, and then do the square of it, okay. So then you add the 2 up to be the final potential energy at the second position. So minus, so this is coming from this gravitational potential energy. You can put those into calculator, it gives you this number. And then the final elastic potential energy will be this guy. Okay, so final potential energy should be negative 127.2 then. Now put all the things in the initial, yeah, then we look at the kinetic energies initially and then final, okay? So kinetic energy initial, because it's released from rest, it doesn't have rotational motion, it doesn't have translational motion, so then T1 is equal to 0. For T2 here, it's going to be having a translational motion, okay, as well as rotational motion, okay? So yeah, so you'll have these two variables here, okay? So T1 is coming from translational motion, 1/2 mv squared. T2 is coming from 1/2 I. So I is 1/12. This is the moment of inertia for a rod, okay? At the center of gravity, 1/2 m r squared, okay? Times omega squared. All right. Now, at position 2, so point A is the instantaneous center of rotation, okay? So then VG2 is going to be equal to the instantaneous center of rotation distance, RG, with respect to IC times omega, okay? So that will give you 0.75, okay, to be the so yeah, it's not the figure is not showing here. Let me show you probably on my paper here. So at position 2 here, we can see that so this is the, okay, So A is going to be here, and then B is going to be here, connected with the spring here. The rod happens to be laying down position as that as well. Okay, so you can imagine when this guy just reach here. Okay, so then it actually this velocity, okay, it's going to be in this direction. This guy is going to be in that direction. Okay. So then this is going to be A, this is going to be B, all right? But at point A over here, when it drops down here, okay, when it gets down over here, this is going to be 0. VA is going to be 0, okay, when it hits this guy here, all right? So then this is the IC for this rod, okay? So it's going to be R of IC is going to be from the center here, G over here. Okay, so R of G to the IC, which is A, point A. So this is this distance, okay, 0.75 meters. Okay, so then VG2 is equal to 0.75 times omega 2. Okay, all right, so then you relate omega and VG2. Okay, so whatever that is VG2, you can write as omega, so 0.75 times omega. Okay, so this is T2. So T2 then is in terms of omega 2. All right, so then T1 plus V1 equals to T2 plus V2. Initially, you will have 0 as kinetic energy, potential energy should be also 0. Okay, T2 is in terms of omega 2, and then V2 is in numbers, okay, minus. Okay, so you can solve for your W2. It's going to be 3.36 radians per second. Okay. All right. Any questions you guys might have? All right. So if not, then we'll look at the second one here. Second one here says this 30 kilogram bra is released from rest when theta is equal to 0. So it's originally over here is released. The spring is unstretched when theta is equal to 0. Okay, so you can imagine the rod was A end is somewhere here when theta is equal to 0. So that's the original unstretched spring length. Okay. It says find the angular velocity of the rod when theta is equal to 30. So you drop this, and then this is going to swing down because the gravity will pull it down. All right. So at theta equal to 30 degrees, what will be the angular velocity of this rod? Okay. So we can examine the scenario over here. So because there will be this force, okay, the weight on the rod and then spring force, that those two forces are doing work. Okay, now there might be reaction force at point O, but point O is being stationary or it's fixed over there. So the two forces acting on the O end of the rod doesn't really do work because displacement at O is 0. Okay, so then only work done is by the two conservative forces of the gravity and then the spring force. So you can apply conservation of energy. Okay, so we'll take a look on the potential energy again. So choose the initial position when theta is equal to 0 to be the data line for the gravitational potential energy. All right, at that position, the spring is at its natural position. So then the potential energy initially should be 0. Okay. Now when the rod is at this second position, theta equal to 30, then VG2 at the second position, gravitational potential energy should be, you are now below the data line, okay, data line. So you are minus mgy. Okay, so y should be at the center over here. Again, should be 1/2 of the whole length times sine of the angle theta from the geometry. Okay, so that's going to be minus 110.4 joules, newtons times meter, that means joules. The elastic potential energy at this point, so you have to figure out what's the length of this guy. Okay, so if this is 30, this is 1.5, this is 2. Okay, so this is 2, this is 1.5, this angle is 30. Then you can use law of cosine to figure out what's the length of the spring and this time. Then, so this is the law of cosine, okay? Law of cosine says, let me see, wait a second. So this one, 100K, right? And then S here, oh, wait a second. Okay. I think this is what this is doing here. So basically, you have to figure out the 0.5 first, okay? So to figure out 0.5 first, it's the original position when this guy is in this position, okay? So the rod was original here, okay? And then the spring is originally here connecting to the rod, okay? So let me pull this geometry on my paper here. Okay, so if this is 2 meters, rod is 1.5 meters, so the original stretch length for the spring should be 0.5. Okay, 2 minus 1.5 S0 is 2 minus 1.5. Okay, equals to 0.5 meters. Okay, and then when you are down here by 30 degree over here, okay, if this is 30 degree here, okay, then the length over here, I don't think, yeah, for somehow, yeah, the PowerPoint slide solution here provided by the publisher doesn't seem to be right, because when you drop this down, this is going to be curved down here, okay? So I think the solution gives us that this is a right angle, but it's actually not a right angle triangle, okay? So I don't think the solution here is right, but for V2, VE2, you should have 1/2 times K times, as I said, you want to use law of cosine here, because this is 2, this is 1.5, this is 30. So then looking at this triangle, you can figure out this length. Okay, it's going to be square root of, if you apply law of cosine, it's going to be 2 squared plus 1.5 squared minus 2 times 2 times 1.5 cosine of 30. Okay, so this is the final length minus the unstretched length of 0.5 square. Okay, that should give you something. I think the number is going to be probably a little bit different than showing over here. Okay, so I'll take care of this later after this class, but doesn't seem like this is right. Okay, so but this is what you want to have to do with this guy. Okay, so this is the right setup for the elastic potential at position 2. Okay, otherwise the rest should be fine. Sorry, I didn't pay close attention to the solution they gave me initially, but now I found that. Okay, so for the final kinetic energy then, okay, so you want to have 1/2 mvg squared plus 1/2 ig omega 2 squared. Okay, so because this rod is rotating about the axis going through O, so then this is 1/2 mvg. You can write vg in terms of omega 2. Okay, so it will be the distance center of gravity 2.0, 0.75, which is half of the whole length. Okay, 0.75 times omega 2. So then this is in terms of omega 2. Okay, so we have T1 V1, T2 V2, then we can apply conservation of energy. So T1 plus V1 should be equal to T2 plus V2. Okay, so this guy, the T2 translational, or it's the both translational kinetic energy and rotational kinetic energy together. V2 should be from gravitational potential energy and elastic potential energy. Again, this number could be a little bit differently. I will figure it out later, but the final answer might be close to this guy or might be a little bit off. Okay, so this is number 2 here. Any questions you guys might have on this one? All right, so if you are clear, then we'll check on one attention quiz here. Yeah, join your breakout rooms again and then work on this one. Then we can look at this one together in a few minutes, okay? All right, so you guys are back. We'll take a look here. So this one says, what's the kinetic energy of the bar when it has rotated through 90 degrees, okay? So when it has rotated through 90 degrees, then it will have rotational energy and translational energy, okay? So it should be D 1/2 mvg squared plus 1/2 ig omega squared, okay? So you guys all got this right, okay? That's wonderful. Now let's take a look group problem solving here. So this one says this slender bar AB is 6 kilogram in mass, 2 meters long. It's originally a horizontal position and at rest. The spring has an unstretched length of 1.5. So spring is unstretched initially, and then spring constant is 12 newtons per meter. Okay, it's asking what will be the angular velocity of the bar when it has rotated clockwise 45 degrees after being released. Okay, so I think we are getting close to the ending time of this class. So let's take a look on the solution here together. I have actually this one pre-written over here. So for attention quiz is D. For this one, so this is the initial position when this is horizontal. This is the final position when this angle is 45 degrees. Okay, so we will take then as this as the data line for gravitational potential energy. So then T1 is at rest is 0. V1 should be also 0 for gravitational energy, and then for elastic potential energy. Okay, this is the initial unstretched length. For T2 then it's going to be 1/2 mvg squared plus 1/2 ig omega g squared. Okay, and this rod is rotating with this axis, so then vg is equal to from here to here half of the length of the rod, v divided by the r, if you call this as r. Okay, or actually no, I'm talking about omega g is equal to vg over r. Okay, rod is 2 meters long, so then from the center to one end should be 1 meter. Okay, so it happens to be omega is equal to vg. Okay, omega and v are the same. All right, and then for v2 g, then it's going to be over here. This is the data line, so this is the y will be minus because you are below. Should be this 2 meters times sine of 45 degree. Okay, so and then times mg. So this is v2g. And then for elastic potential energy should be the length of the spring minus its initial length. Okay, so the length of the spring from the geometry here, you can see this is the hypotenuse of this right angle triangle. Okay, where this is 1.5 plus this amount. Okay, so it's the 1.5 plus 2 times sine of 45. Okay, and then this guy should be 2 minus 2 times cosine of this guy. Okay, so the whole length minus this length. Okay, 2 minus 2 cosine. Okay, square. So a squared plus b squared square root, and that's the hypotenuse. Then the stretch length for the spring should be this whole length minus its original 1.5, 1.473. That gives you the elastic potential energy. Okay, so we apply conservation of energy T1 plus V1 equals to T2 plus V2. All right, 0 plus 0 plus equals to, this is the rotational kinetic energy. So I actually express this in terms of rotational energy about this point A. Okay, you can do either this and that. Okay, so this is rotational translational energy about G, and then rotational energy about G. Or you can do just pure rotational energy about this guy. Okay, so either way, you're going to get this right. Okay, but because if I just look at this point, then I'll be doing just rotational energy about point A. So then I only have one variable here to solve for. Okay, so I plug in all the numbers. I solve for the omega to be 2.67. Okay, that will be the final answer. Okay. questions you guys might have before we actually finish today's lecture? All right, if not, then that's it for the lecture. So I really enjoy spending the whole semester with you guys. I like this class very much. I like you guys very much. So thank you for spending the time with me. So for some of you guys, we'll see you next semester and then in the spring semester for some of you guys. But for some of you guys, we are probably going to see each other on campus, but not in class, no. Or I hope that you will take modern physics to get the physics minor so we can still see each other in the classroom, okay? Or you can help me in the physics lab, okay? So we can still see each other, all right? Otherwise, good luck on the final exams, okay? I'll see you guys later at some point, okay? Bye, guys.
Dr. Ho,
Yes.
Thank you.
that modern physics class, is that likely going to be in the fall or the spring semester?
It's usually in the fall semester, but if you are interested, I think we can do independent study or something like that. So that can be flexible. Okay.
Okay.
Yep. So yeah. If you are interested, you can talk to me later about this.
All right. Thanks.
All right. You're welcome.
Thank you.
You're welcome, Macy.
See ya.
Yeah.